A question was brought up about solar eclipses inside LSC Earth. And the question was, like, if the moon... Let's bring up my screen here. That's a good shot. Okay. If the moon... Okay, here we're looking at this diagram. Top down. Let's zoom out a little bit so you understand. Okay. So we have the celestial sphere here. We have the octahedron looking top down. We have the sun here and the moon in front. The path of the sun is a yellow dotted line, and the path of the moon is the blue dotted line. So we have my sun here, and we have different positionings of the moon. And you'll notice it's a funnel-shaped illuminated area that projects outward from the sun. When the light from the octahedron hits the back of the sun, and it flays out like that, it disperses out like that, and so it creates this funnel-shaped area. And so one of the questions was, like, if the moon is like over here somewhere, why wouldn't we get the shadow of the moon appearing on the land? And that has to do with the angle of the light and the way the trajectory works, how it curves around like that. So I have 3 different scenarios of the positionings of the moon. If the moon is here, in other words, outside this funnel illumination zone area, no shadow will hit the earth. If you look at this gray dotted line, that's the path of the light. It's not hitting the earth, it's simply just wrapping around like that. If it is intersecting with that funnel illumination zone, that's when we get a partial solar eclipse. And so the partial solar eclipse, let me get my layer up here, it's going to project a shadow area where the shading is going to bend around like that. And so this area over here on the earth, or in the earth, is going to be shaded, and it's going to be what you would call a penumbral shading, not the umbral shading. The umbral shading is where it's darkest, and so we're not really going to get much of an umbral shading with the partial solar eclipse. And of course, the total solar eclipse, this positioning right here, the moon, it's going to project your shadow here, going straight up like that. Okay, hopefully that clarifies how light works, how the solar eclipses work within the Earth. It all has to do with the curvature of the light and the trajectory of the light and the illuminated conical zone area. It doesn't take much for the moon to exit that area. In other words, it's a very narrow region here. So if the moon is even just slightly offset with the sun, you're not going to get a shadow on the earth. Okay. Hopefully that makes sense for you guys. Okay. Hi, I'm making an addendum video to my previous video where I talked about the total solar eclipses happening within LSC Earth. And what I was showing you previously, let me pull up that graphic here, this graphic here, and I said it was looking top down. And so what I did not show you is how the total solar eclipses were happening in the polar regions. If you look at this graphic here, you'll see that we have total solar eclipses happening, obviously, in Antarctica. The blue regions are the red regions. The red regions are annular, and the blue regions are total. And so, I went back to Illustrator here, and I pulled up, actually I made this graphic here. We see the octahedron in the middle, side view. We got the equator going straight across. We got the high arm of light hitting the back of the sun. And then I created these little orange lines. I call them scope of view lines, basically. So if you're standing here at, let's say, negative 23.5 degrees, your angle, your view of the eclipse is going to be happening when the moon is going through this orange, this little shoot here, basically. So if you're standing on the South Pole in Antarctica, obviously, the moon would have to be lower in declination, which I have it over here. And so you're still, what I did was I expanded the orbital path of the moon. I made it closer to the Earth, and we have a little bit more elbow room here, basically, where the moon is traversing through that conical zone of illumination. And it just matters where you are situated latitudinally within the Earth in order for you to see that. So it's about trajectory, and it's about point of view and reference. And so that will help you understand better how we can see total solar eclipses happening wherever you are within the Earth. It just happens to be where you're situated and how that scope of view aligns up with the moon and the sun. And obviously the partial solar eclipses are going to be happening, as I mentioned before in my previous video, where the moon is going to be partially or just interfering with that edge of that illumination zone. Okay, so I have here in text, if the moon is higher in declination, the scope will align in the total eclipse to be visible in the tropic zone. So that I have that over here, and then this one over here. If the moon is lower in declination, the scope will align the total eclipse to be visible in the polar region. And so that would conversely go over here as well. If the moon was over here, we would get this total eclipse happening higher north, way up here. And of course it matters where the sun and the moon are situated in declination. Like right now I have the sun at minus 23.5 degrees, so this is at the winter solstice. So, okay, hopefully that makes sense. Thanks for watching. Okay, this is a more polished version of the solar eclipses within LSC Earth. Previous video I made, I forgot to change the orbit of the moon because we're looking at the side view, so let's bring that up here, and we'll see the horizontal blue lines that indicates the moon's cylindrical orbit, and the horizontal dotted yellow lines indicates the sun's cylindrical orbit. And as I mentioned previously, I indicated these little shoot zones with these orange lines. So whatever latitude you are at, you're looking at the sun through this little scope zone. So if you're over here, let's say this is at like negative, I don't know, 8 degrees, or actually this is negative 23.5, I'm sorry. And the sun is directly in front of the moon is directly in front of the sun, we're going to get a shading right there. However, if the moon is a little bit lower in declination in this little illumination zone, it's going to carry the moon shadow at a more extreme latitude. So I brought that into 3D here, and so I morphed the moon shadow so you can better visualize what's going on here. As you see, as I scroll across the timeline, the shading is morphing, and the declination of the moon within that illumination zone is really critical as to where it's going to project the shadow on the Earth. If it's a little bit lower in that zone, it's going to project it like that. Let's say the sun, like I'm actually rotating the sun as well here, so this is like, maybe this is like, I don't know, negative 10 degrees or so. And if I scroll a little bit more, it's going to get more extreme like that, and that's how we're going to be able to pick up a shade zone in the very southern polar regions, or the northern. I just did the southern for this video. And of course, as I mentioned before, if that moon leaves that illumination zone, let's say the moon is right over there, it's not in the illumination conical zone anymore, so that moon shadow is going to wrap around. It's not going to hit the Earth, and it's going to curve around and converge to the other side, very similar how the sunlight converges to the other side and creates the Gegenschein at the anti-solar point. So there you go. I think this helps understand, helps visualize what is going on with the solar eclipses inside the concave cellular LSC Earth. Alright, there you go. Pretty cool. Thanks for watching.